We're going to continue our discussion on design principles. We talked about a few metrics and we talked about a few principles already. We talked about the Yagni principle, the single responsibility principle, the DRY principle. But it's going to get only more exciting and interesting as we move forward. We're going to talk about some very fundamental principles in this presentation and a few that follows this. We're going to talk about some principles that can help us to create extensible software. Now, to create extensible software, it is not that we have to do more. Sometimes we have to do less. Sometimes we have to keep an eye on the things we already talked about, like cohesion and coupling. But it's nice to really put that into a little bit more of a formal framework so we can think through that and understand the ramifications and the consequences a little bit more easier. So let's talk about the nature of software to begin with. Now, it doesn't matter whether a software system was developed in a nice way or in a poor way, it will have to change. The change is not based on the design of the software, the change is based on the external influences. The project needs change, the environment changes, the user expectations change, the requirements change. We have to accommodate a certain new set of rules and laws and various other things that change around us. A new feature is requested by a user often, or a feature that we implemented is no longer quite applicable, or there are some variations to data types we can support. There are so many different things that can influence change on a software. Now, if somebody comes to you and tells you that they designed a software, but after they designed and implemented it, they never had to change it, what they are telling you is, what they are hinting is, the project got canceled. So any relevant software has to really evolve, has to change. But when it comes to change, when such a change comes through, a software system has to really change to meet those change in requirements and other things. So whether the software was developed in a good design or a bad design, it will have to change. But there is one big difference though. A good software is like a tennis ball. A software will change, much like a tennis ball. When you drop it, it'll go down. But the difference though is, just like a tennis ball, a good software is resilient. It'll bounce back up. So notice if I throw this tennis ball, it's going to bounce back up. Much like that, a good design will change, but it's resilient. It'll bounce back up. So without an enormous amount of cost, money and time and effort, we can make the software evolve fairly quickly. But on the other hand, a bad design will also have to change, much like eggs that you take on hand and drop, they would have to go down. But the difference is, when these eggs go down and hit the floor, they don't bounce back, they leave a GUI on the floor, a mess to deal with. And it's extremely difficult to put them back in shape, and a bad software is just like that. So both a good software and a bad software change, but a good software is resilient to change, whereas a bad software really does not respond well to change. And it becomes expensive to evolve a bad software. So the question is, how could we create better software? One way to create better software is really to structure the system in a way that we can extend the software without actually changing pieces of the software. Now that's very confusing. How could you extend a software without changing some parts of the software? That's what we're going to talk about in the next principle, called the open-closed principle. Bertrand Meyer coined this principle called the open-closed principle, and he says software entities, where an entity could be a class, a module, a function, just about anything. A software entity must be open for extension but closed from modification. How in the world can a software system be open for extension but closed from modification? Now, how could we make this do something more than what it did before, but without actually changing it? Well, therein lies the ability for us to create a software, and that's basically called the open-closed principle. Now, a software is going to have to change as the requirements change if that software is tightly coupled. So if my class is tightly coupled to another class, and if I don't want to use this class anymore, I have to change it. or anytime this class changes, my software may be affected by it, my module may be affected by it, my entity may be affected by it. So one way to make sure a software is extensible is really to rely upon an abstraction and not depend on the concrete type, but on an abstract type. So in other words, the open-closed principle says, if you want a software module to do something more than what it did before, make sure that it doesn't really tie to something extremely concrete and specific. Let it depend on something a little bit general enough. This again goes back to the Postel's law we talked about. Be generous about what you receive. If you're specific about what you receive, then you have to change your code when that specific thing changes. If you are general about what you depend on, you have to change your code less, and you're going to be more accommodative. So you can see how these things kind of relate to each other. Open close principle and Postel's law kind of go hand in hand at that point. So given this, let's talk about this with a certain example of what this principle actually would mean. So a characteristics of a poor design is, it's a design that has to constantly change. Any little thing changes it. That's fragility. Or it's very difficult to make a change to it. In other words, a system is rigid. So a poor design could be rigid, a poor design could be fragile, and sometimes a poor design is unpredictable. A little change here ripples through a cascade of change, and we cannot predict how many changes we have to make and how long it's going to take to complete this change request. However, if you really think about it, if I ask you to do one of two things, let's say, I bring a piece of code to you and say, here is a piece of code, and I want you to read this piece of code, understand this piece of code, and modify this piece of code. That's option number one, I'm giving it to you. Option two, I'm giving it to you is, here's a piece of code, you don't have to touch it, you don't have to change it, but simply write a very small module of code and integrate it, and everything will still work, and your application is more extensible than it did before. Which option would you rather choose? Option one, where you have to go back and change existing code, or option two, where you can add a light small module of code and be done with it? And I'm sure you would agree, option two appears more tempting in this case, because I don't want to change an existing code. It's fairly easy to just add a little module of code and be done with it. In a way, for example, if I live in a house, I can ask somebody to come and make an addition to the house, maybe add a new room, or maybe convert the basement to a series of rooms, or I could have them build a little room outside the house as an annex. Now, which one is going to be relatively easier for us? Well, affecting the existing building takes a lot more effort. You got to be more careful than doing it outside. So you can draw a similar analogy, however crude it may be, to software development as well. So let's look at one example of this to see where the consequences would be. So I want to start with a little example. Let's say we have a class called a car. And the class car is going to have, let's say, a private int year as a variable. So we're going to decide when the car has been created. So I'm going to go ahead and create a constructor here. And the constructor I'm going to create simply says, in this case, year equals the year, where the year is just a parameter that I'm going to bring in for the year itself, for the class itself. So right there is the year that comes in as a parameter. So I'm also going to go ahead and create one other function. We're going to provide the toString method. And in this method, I'm going to simply return, let's say, the word car, followed by, I'm going to return the year of the car's manufacturing. So let's build on this example. I'm going to say car1 equals new car. Let's say this is going to be a car that was created in, let's say 2015. So I have created a new car object, in this case given a year for this particular car to be created. So once I have a car object, what am I going to do with this car object? Well, I want to go ahead and just print out the details of the car for now. Let's simply say car1 and have the car1 printed. Now, in this case, it's giving us an error. Let's take a look at it. It says this cannot be referenced in a static context. Of course, I'm going to move this into a separate class outside of this class. So let's go ahead and create a separate file with the car class in this case. So I'm going to keep that over here, but I'll come back to that. So let's go ahead and create a car class. So let's go ahead and say, create me a class called car. All right. And this car class is going to be the car we just created a minute ago. So that is good enough for us. Now that we created a car, I want to add a little bit more to this particular car. We're not done creating this car yet. So I'm going to say, comma, new engine, and I'm going to introduce an engine to this car. Let's go ahead and create what this engine is. So I'm going to go ahead and create a new class called engine. Well, I don't want to use that particular engine. That's funny. I don't want that particular engine. So I'll go ahead and create another engine. We'll come back and rename this. I'll just say my engine just for a minute and we'll refactor that. So I'm creating my class called my engine. And what am I going to do with this particular engine? Well, let's go ahead and say you rename this particular engine to some other name, if you will. So let's go ahead and say refactor this particular name engine. And rename it, and that's a Shift F6. That's what I tried to click a minute ago, and that was complaining for some reason. Let's try it one more time. Shift F6, and I'm going to say engine. There we go. So I just created that. So now that we called it as an engine, what am I going to do with this engine now? Well, before that, we need to modify the class over here, the constructor, to receive an engine. So let's go to the constructor of the car and say, comma, and I'm going to say engine, and we will say an engine. So once we receive an engine, I'm going to say equals an engine, and I want to save this away into a field. So I'm going to create a field called the engine field. So there we go. We created an engine field and saved it. So once we have saved this value, let's go ahead and create this over here to say what the engine is. So I'm going to say plus, and then we will also provide engine dot, let's say toString, and just propagate up the chain to the engine class to print it. But what does the engine really have at this point? Well, the engine doesn't have a whole lot right now, but let's go ahead and create, in this case, just a little bit of a detail here to say I want to print the engine. So in this case, I'm going to go ahead and print the return. Let's go ahead and say get class, and I'm going to return the class detail of the engine. That's all I'm going to print out at this point. So if I go back to the main and run this code, you can see that it says class car is 2015 year, and it says engine for the information about the engine. Well, we're good so far, but let's continue a little bit further with this. Let's say I want to make a copy of this car. So car2 equals, and I'm going to say new car2, in this case car1, and I want to output, in this case, the car2 we created. So right off the bat, you can see Java complaining that I cannot pass a car1 to the constructor of car, and the reason for that is the constructor of the car requires a year and also the engine, and obviously I cannot pass just another car object. If this was C++, your code would compile with no errors, and the reason simply is C++ provides a default copy constructor. What does a copy constructor in C++ do? It causes nightmare, and it causes a really pain. And so with all the trouble that C++ created with copy constructors, both Java and C# said, no copy constructor for you. But that doesn't stop us from creating our own copy constructor if we wanted to. So I'm going to go to the car class and say public car, and I'm going to say car other car in this case. And of course, what I want to do is say year equals other dot year, and I'm going to say engine equals other dot engine, but we don't want to do that, because we don't want the two cars to point to the same engine. We want the two cars to have their own copy of the engines. So we're going to say engine equals new engine, and then we're going to say, in this case, it's a copy from the other car's engine. That requires us to go ahead and write a copy constructor for the engine. So we're going to say here is a constructor for the engine, but we're going to also create yet another constructor where this constructor for the engine, the second one we are creating, is going to say engine and other, And all that it has to do simply is to just not do anything at all. There's not a whole lot to do within this particular engine, so we'll just leave it like that. I don't even have to call a super in this particular case. We can just leave it. I don't care to really pass anything up to the base. So now if I go back and run this code, we can see in this case, we have two cars and we have the engines of the car. Well, just to be sure that they are two different cars actually, let's go back to the toString method and say plus, and then we will also provide, let's say, the hash code, just to be sure we really are getting two separate instances of the engine, and sure there are two cars, and notice the instances of the engine are different. If the hash code is different, we know the objects are different. If the hash code is the same, we cannot quite say whether they are same or different. So in this case they are different, so we know that it's different. So it seems to be working, right? So what's the problem? Well, the problem is, if you look at the car class is tightly coupled to the engine class. Engine is concrete and car is concrete also. Now the question is, what are we, the dependency is not just here, the dependency here also. But let's understand what the consequence is. Let's say a few weeks goes by and we are told we no longer want to have an engine, we really want to use a turbo engine. So now if I create a turbo engine, so let's go ahead and say we have a class called a turbo engine, and smartly the IDE found out it extends from engine. But let's go ahead and create the constructor for the turbo engine. Let's also go ahead and create the copy constructor for the turbo engine. So we took care of those two details right here. So now we can go back to the code and run it. And oh my goodness, look at that. While the first car has a turbo engine, the second car ended up having just an engine. We feel really cheated on this, isn't it? We made a copy of the car in good faith, but it really did not make the right copy. It cheated and provided a turbo engine for the initial, but only an engine for the second one. So how do we fix this particular problem? Well, here's an idea for fixing this problem. I'm going to go to the car class and say, aha, new engine. New is not polymorphic in Java and C# and C++, but new is actually polymorphic in a language like Ruby. But because new is not polymorphic, this is binding to the very specific class in this case. So what can we do to get around this problem? I got a bright idea. You will love this. I'm going to say if the other classes engine is an instance of turbo engine, then I want to say engine is equal to, and this is going to be a new turbo engine. Otherwise, I'm going to make this a engine. And of course, this has to be cast to a turbo engine. And I'm going to say, in this case, it's other.engine to provide the engine value. Now let's go ahead and run this code and see what the code is doing. And notice that, voila, both of them are turbo engines. But if I were to use an engine instead of turbo engine, then both of them are engine. So depending on the type we used, we either get turbo engines or engines. Problem is fixed, isn't it? Wait a minute, you say. This code is really ugly now. And what's the problem with this code? Well, you have a turbo engine and you're checking to see if it's a turbo engine. But what if a few weeks goes by and we introduce a different engine, not a turbo engine or an engine, we just introduce a piston engine, for example. Now I have a class called piston engine I just created, and the piston engine also inherits from engine. And now that these two guys inherit from engine, I come back and run the code, and guess what happened? We're back to the square one of the problem. The original has a piston engine, and our copy ended up, how sad, with the regular engine. Well, to fix this now, we have to go back here and say, if it is a turbo engine, then use a turbo engine. Else, if the other.engine is an instance of piston engine, then go ahead and create a piston engine, because that's what the type here is. And so this is going to change to a piston engine. And then this, of course, is going to become a piston engine as well. Otherwise, one more time, else, And what are we going to do within this else block? We're going to say, now go ahead and create a regular engine in this case. And then if we go back and run the code, the problem is gone again. But notice that for every class we added into the hierarchy of the engine, we had to come back and change the car class. So in other words, in this example, the software entity, which is car, is open for extension. Sure, the car worked with the engine, a turbo engine, a piston engine. It is open for extension, but unfortunately, only through modification. We had to change the car over and over and over for us to be able to accommodate this change. But I want you to look at the bright side of this. This is not bad. This is something, if we continue to do, gives us really nice job security, isn't it? Well, after a while, you're going to hate that job and you don't want to be doing this anymore. So this is fundamentally a poor design, and this is considered to be a violation of OCP, or open closed principle. So anytime you hear me say this is a violation of OCP, what that means is that the code we wrote is not extensible without having to physically modify. In other words, adding a change or changing a type outside will affect another piece of code, and we want to make sure that code is compliant to OCP. In other words, as many times as you add another piece of code, you shouldn't have to come and change your existing code. So how do we make sure that this code doesn't have to change constantly if we are adding new pieces of code? Well, one way to do that is to rely upon polymorphism. So the key really here is that if you really want to do this, the software module must be open for extension, but we should be able to extend it without modifying it. It should be closed from modification. So to do this, you don't want to really depend on the concrete class and be affecting it. So the better way to do this is to really use abstraction. So you can create an abstract engine, and you can have these rely upon the abstract engine. And what would this give us? Well, the class, really, the idea is a class should not depend on another concrete class. Instead, it should depend on an abstraction. So what will happen if it depends on an abstraction? Well, we then get to use abstraction and polymorphism, which is really the key to extensibility. So notice what I'm going to do in this particular example. Originally, we said engine equals new engine, and then we said other.engine. That did not work. Then we used the if else with the instance of, and that did not work also. So what we're going to do instead is, in this case, we're going to say engine equals other.engine.clone, and we will call a clone method on this particular engine. So in this case, notice we are calling a clone. Well, the clone in Java itself has some little problems in it. So rather than using the clone, let's just say make copy over here. Because that way we can avoid the discussion about how broken Java's clone is. We don't have to worry about that detail right here. But instead, let's focus simply on the copy, make copy method. And if you're really interested, we can talk about why clone is broken in another presentation separately. But let's make this very simple. So now I'm going to go to the engine class, and I'm going to create over here a public engine, a make copy. And what is this method going to do? It simply says return new engine this. So when you call a make copy on an object of engine, it turns around and calls the copy constructor and makes a copy using the copy constructor for the engine. And so as a result, you can see in this case, the car is simply calling on the make copy. And of course, in this case, I don't even have to cast because it is returning an engine. But how does this really help? Well, make copy is a polymorphic method. So as a result, notice on an engine, make copy is making a copy of the engine. But I'm going to go to the turbo engine and I'm going to implement, pardon me, I'm going to implement the make copy method in the turbo engine, but here I return new turbo engine this, And likewise in the piston engine, I'm going to go back here and say implement the function called make copy, and in the make copy method I return new piston engine this. So in other words, polymorphically, an engine makes a copy of the engine itself in the make copy. The turbo engine makes a copy of a turbo engine in the make copy. And piston engine makes a copy of a piston engine in the make copy. But because make copy is polymorphic, depending on the runtime type of the object and not the compile time knowledge of what the object really is, we will end up calling the make copy on the appropriate type of the object. If at one time the other car's engine was a piston engine, this will call the make copy on the piston engine. If the other car's engine was a turbo engine, it would call the make copy on the turbo engine. So now if we go back to this main code and we simply send only an engine and run the code, notice that both of them are engine. We now say piston engine, run the code, notice both of them, oh wait a minute, yep, there we go, it scared me for a second with that little pop-up. Yep, that's a piston engine. And finally in this case we have a turbo engine and run the code, and what does that do? Notice it's a turbo engine. Now if we were to really create yet another engine, we'll call it as super efficient engine. Now that we created a super efficient engine, notice the changes I'm going to make. I made a change to sample here. That's a main function that has to change to know what we are going to use, unless we go to extreme measures of abstracting that out to configurations. But I added a super efficient engine. Now I'm going to go ahead and create a super efficient engine. And what am I going to do? That's a new module of code we are creating. And in this case, I write the constructor, the copy constructor I'm writing, and of course I'm writing the make copy method where I return new super efficient engine this. But notice I did not touch any existing code. I did not touch the engine. I did not touch the car, more important. And I come back to the sample and run the code, and notice that both of them have a super efficient engine. And so car now is extensible for a new engine without request for modification. So this shows us how a particular object can be extensible without having to physically change. And we accomplished that in this particular example. Now we can make a few other changes to this particular example just to make this a little bit better. We can make the engine itself an abstract class to begin with. So we can say this is abstract, and the minute you make it abstract, you cannot create objects of that. So I'm going to make the copy, make copy itself an abstract method right here. So I don't have an implementation of the method over here in this case. And then what am I going to do after this? Well, now that I have made the make copy an abstract method, what do I need to do in the turbo engine? Well, in the turbo engine, I don't need to make any change. And so let's go ahead and run this code and see what it's going to do. And sure enough, it's still working. And again, we can pass a piston engine, for example, and that's working. Of course, we cannot create an object of an engine because we made an abstraction out of it. You cannot create an abstract class out of it. We cannot create an instance of an abstract class. Likewise, if you will, there's one other change we can make. We don't really want this to happen, where we come in to the car and even by accident say engine equals a new engine, and then start creating an object of engine like this. So how do you prevent a call to the engine's copy constructor from within here? Well, obviously because it's abstract, you cannot create an object of engine. That works really well. But what about new turbo engine? Aha! Notice that did not stop us from doing it. How do I make sure this doesn't happen? In other words, how do you emphasize that only make copy should really be called? Well, we can go to the engine class and we can make the engine a protected method. And then we can go to the turbo engine and make the turbo engine a protected method copy constructor, that is. And we can make the piston engine's copy constructor a protected method. Because it's protected, the derived classes can access the function, absolutely, that method. And we make this protected as well. But now if I come back to the car class, well, because the car is in the same package, unfortunately in Java, the protected is accessible across packages. But if I were to change this package as cars for a minute, so I'm going to go ahead and move this into a separate package. So let's go ahead and try that and see what is going to happen at this point. So let's go ahead and say engine example.engine multiple choices. Well, it's obviously complaining it doesn't know what an engine is. We can help him with what the engine really is. So let's go ahead and say bring that in. So it's importing that for us, actually you can see. But let's go ahead and fix this over here. Well, let's fix the turbo engine before we go further. But notice now, in this case, he's complaining on turbo engine. But we'll come back after we fix the package problem here. So move to this package called cars. And sure, I want to move that into the source directory. So it moved into the cars directory. Now notice what the error is. It tells us we cannot access the protected constructor, copy constructor, and turbo engine from within the car, and that way we don't accidentally call it. So going back to this example, to summarize what we did, our engine is abstract, our engine's copy constructor is protected, we got a method to copy or clone that object, that's abstract too. Then in each of the derived classes, we overrode the copy constructor and implemented what we need to. We provided the make copy method or the clone method, we overrode it and turned around call our own copy constructor. So as a result now, the objects like car can rely on polymorphism to create the object, and at runtime, not based on the fact that this is an engine reference, but based on the runtime type of the engine, other engine, it calls a write make copy, and as a result, in our code, we end up getting the right kind of object that we are actually creating. Now, of course, in this case, we moved the car class, so he's complaining. We'll go ahead and import the car class in here. So we'll bring in import, and then this is going to come from example over here, dot cars. And now that the car is going to come from that particular package, as you can see, and that's where we're going to get the car class from. Let's go ahead and examine the package here just to be sure we have the right stuff on our hand. So here is the source, and we have the cars right sitting here, and the car class is sitting right there within that. Now the sample, of course, needs to bring in that particular car object. So this is going to be example. Let's make sure it's bringing in. So example.cars. And this is going to become the car. Let's actually examine to make sure why he is complaining with the car class is not bringing it in. So that's basically the car. We don't depend on the turbo engine anymore, obviously. So that is still good. And he's complaining that the car is never actually being used. Well, that's what I'm trying to do, silly code here. I'm actually trying to use the car class, and it's complaining. We'll come back to that in just a second. So I'm going to say car over here. So examples over here, example. And this is going to be dot cars, and of course it doesn't show up. I think I know the reason for that, because I did not make it public. There we go. So now let's go back here and say that's the class I want to use, and you can see that that's coming through the car class. Now that we have a car class on our hand, we make a copy of the car, and then you can see that in this case, you could extend this logic further to say, well, car should not have a copy constructor per se. It should also use something like a make copy, and I totally agree with that. So you would make the cars constructor, copy constructor protected, write a clone or a make copy method, and then you can use that method in here. In fact, let's go ahead and do that real quick. I make this a protected method, as you can see. Then I write a public over here, car make copy, which is really the clone method. And I'm going to say return new car this, same logic we are using in this case. And now I go back to the sample, and to get a new car, I say car1.make copy. And of course, we made a copy, and you can see these two are having piston engine. But again, as you can see, if I make a change to a turbo engine without changing the car anymore, we can get this working really nicely. So that shows us that open-closed principle relies upon the abstraction and polymorphism as the very key principles. We got a lot more to talk about open close principle, so we'll talk about that in the next part of this presentation.